Hi, welcome back to Chem 3 at Richard Stockton College. This is the second semester of organic chemistry, and in this lecture I'm going to review some of the reactions you should have learned in last semester's class. If, for any reason, any of these reactions are unfamiliar to you, perhaps, for instance, you took Chem 2 at a different institution and they cover something in second semester that we cover in first semester or whatever. Those might be places you want to go back, look at the text, and then come talk to me in office hours. I'm going to cover a lot of material very quickly, so I'm really just going to be highlighting things in an effort to jog your memory and point out some of the key things from last semester, rather than trying to explain the reactions in detail. Okay, let's move into it. Before we can start looking at reactions themselves, there's some basic terminology that you need to use when talking about reactions. On this slide, I show a reaction energy diagram. Along the x-axis, down here, we see the progress of the reaction, starting from the starting material. If I have a multiple step process, this curve shows a two-step process, going through any intermediates, and then ultimately to product. The y-axis is showing the energy of the reaction. Organic chemists tend to be a little bit sloppy when talking about energy. There are various different units that could be used. For instance, Gibbs free energy, or delta G, or enthalpy, delta H, are the two most important. In other classes, you would be very careful about which units are being used and being quantitative about that. We're going to treat energy a little more broadly and qualitatively, so I won't make careful distinctions much of the time about whether I'm talking delta G or delta H. You'll notice there are 5 points of interest along this reaction energy diagram path, the purple line. The starting material and the product are obvious. Intermediates. Many reactions, well, some reactions are one step. You might recall things like the SN2 and the E2 are one-step processes. I'll mention those in a little more detail on a subsequent slide. But other reactions happen in more than one step. First one bond breaks, and then there's an intermediate, and then some other bond change occurs, for instance, like in an SN1 or an E1. Again, I'll see those in a moment. In such examples, we'll have one or perhaps more than one. I'm going to show a 7-step process by the end of this lecture. That one has 6 intermediates, so there's a bunch of different points along the way. Intermediates are things like carbocations or carbanions usually. They actually do have some inherent stability in that that exists for some amount of time and could be directly studied, at least in principle. On the other hand, there's these transition states. In the course of a reaction, some bonds are broken and others are formed. A transition state is a place with incomplete bonding. That is, one bond might be starting to break and another one might be starting to form, or some number of bonds might be breaking or forming at any given transition state. Transition states have no inherent stability. The molecule does not spend any real time at that point. It's simply the transition, moving from here to there. And so you can't directly study transition states, but they are the high points along a path between low points. When the rate of reaction, as I'll mention on a next 2 slides down the road, is related to the transition state, and in particular, when there's more than one transition state, the highest energy transition state turns out to be what's called the rate determining transition state, or the rate determining step, sometimes called the rate limiting step. That means the same thing. All right. Energy really comes in 2 flavors in chemistry. We often talk about thermodynamics. Thermodynamics is pretty much comparing the starting point to the ending point and deciding whether or not the starting point is higher in energy than the ending point or lower in energy than the ending point, and by how much. This is characterized by the change in energy. Here I give Gibbs free energy, delta G, being the Gibbs free energy of the product minus the Gibbs free energy of the starting material. That is, if the starting material is at a higher energy and the product is at a lower energy, a smaller number minus a bigger number is always a negative number. So if I'm going from a higher point to a lower point, the delta G is negative. Vice versa is also true. So if I'm going from a lower point to a higher point, this number is a bigger number minus a small number, so delta G is positive. A reaction is going to be favorable. The term that is used is spontaneous, though that means something a little bit different than if you use the word spontaneous outside of a purely scientific context, if it is downhill. In general, reactions that are downhill will occur without having to add a lot of extra energy. If a reaction is uphill, you have to somehow put energy into the system to get that to go. I'm leaving aside activation energy, which I'll get to in a moment. But overall, the energetic change is favorable for a negative delta G reaction. Delta G can be divided into a couple of terms, delta H and delta S. The enthalpy of reaction is one way of describing it would be the energy of bonds. When you talk about the energetic change in a reaction and you're forming some bonds and breaking other, if you are making stronger bonds or more bonds, your delta H is going to be downhill. That is, the difference in enthalpy between the starting material and the product. I really should say the difference in energy between the product and the starting material will give you a negative number. So if you're going from a higher energy to a lower energy, that means you're getting to stronger bonds. So the more strong bonds that you form in the course of reaction, that's more negative delta H, the more overall negative your delta G will be. Or in other words, the more favorable the overall reaction will be. On the other hand, there's this entropy term, delta S. Entropy has to do with randomness. And the more you break bonds, the bigger your entropy gets, the more random your molecule gets. Because if you had one piece and you broke it into two pieces, that's more random. And therefore, the more bonds you break, the more your delta S term gets bigger. But since there's a negative here, and the T is temperature, that also helps favor negative delta G, which is a more favorable reaction. Whether a reaction is favorable or not turns out to come from the balance between these delta H and delta S terms. Bond breaking makes delta H more favorable. Bond making makes delta H more favorable. Bond breaking makes delta S more favorable. Since there's the temperature multiplier with the delta S term, at higher temperatures, entropy becomes more important to the overall energy of the reaction. At lower temperatures, if this was zero, so at absolute zero, 0 kelvins, this term would disappear altogether and delta G would simply equal delta H. Even at room temperature, the delta S term becomes less, not so important, and the delta H term really dominates, which is why organic chemists tend to be a little bit sloppy in terms of whether we're talking about delta H or delta G. If a reaction is downhill, in terms of delta G we call it exergonic, and in terms of delta H we call it exothermic. If it's uphill, the term in terms of delta G is endergonic, and in terms of delta H is endothermic. I will use those terms. I'll probably use the term exothermic and endothermic for a downhill and uphill reaction without, again, just warning you in advance, being a little bit imprecise about which unit I'm using. I'm being a little bit more qualitative when I say that. These terms, delta G, delta H, and delta S, are what are called state functions. That is, they're simply comparisons between the start and the end. And the path that we take doesn't matter when talking about these. They are path independent. The path is not related to thermodynamics. Thermodynamics is simply, I start here and I end there. And if the ending is lower in energy than the starting, that is overall favorable. But you know what? Some reactions that are favorable still happen very slowly, and other ones happen very quickly, which is why I said the word spontaneous in this context might not mean the same thing that you're used to it meaning. Because sometimes a reaction might be spontaneous in the sense used in thermodynamics, and yet still be a very slow reaction. The rate of reaction is related to the path. So kinetics describes the rate of reaction. In kinetics, we talk about rate laws. The rate of reaction is equal to some rate constant times the concentration of reactants. So there's a couple of things affecting the rate of reaction. One is the concentration of reactants. If you think of reactions as a bunch of molecules bouncing around in a space, the more concentrated they are, the more often they will run into each other. Just like you will run into people more often in a crowded room than in an uncrowded room. And therefore, when molecules run into each other, that's when reaction can occur. So more concentrated equals faster rate, less concentrated equals slower rate. But there's also this rate constant. But that rate constant can be further examined. To break it down, this is the Arrhenius equation. Not that we, again, this is organic chemistry. We're going to be treating things more qualitatively. So I'm not worrying so much about the quantitative discussion of these formulas. I just want to make some points about it. The rate constant is made up of these terms. This A, don't worry about it, it's a constant. This E, that's the E that's used in natural logs. This R is the gas constant. So those are all constants. But there's two other things here. EA and T. T is temperature. So whether it's a hotter or colder set of conditions, that will affect the rate constant. The way this formula is set up, at higher temperature, you get a higher value for this rate constant, and since that's used here in the rate law, you get a faster rate. Higher temperature, faster rate. Lower temperature, you get a smaller value for this K sub r, the rate constant, which means you get a slower rate. So you can speed up a reaction by heating it up. On the other hand, there's this term, EA. EA is the activation energy. It's the height of this curve, from the starting material to the height of the transition state. And if I have more than one step, it's the height of the rate determining. That is the highest energy transition state. The higher this barrier is, if it's like way up here, you're going to need to put more energy in to get reaction to go. If the barrier is lower activation energy, you don't need to put much energy in to get the reaction to go. The higher that barrier, the slower the reaction. In this formula, the bigger this number, the smaller this number, the smaller this number. So I don't want you to worry so much about the details of these formulae, but I want you to realize that the barrier of reaction is related to the rate of reaction. High barrier, slow reaction; low barrier, fast reaction. Temperature also affects the rate of reaction. High temperature, fast reaction; low temperature, slow reaction. And the concentration of reactants in the rate determining step affects the rate of reaction. More concentrated, faster reaction; less concentrated, slower reaction. We've already described transition state, but just to rehash that thought, it's the high point. You can't put transition states in a bottle. They have no inherent stability. It's sort of part way along where some bonds are starting to break, and other bonds are starting to form. We also can talk about equilibrium, when a reaction is reversible. And I should note that technically all reactions are reversible. It's just in some cases the forward reaction is really, really, really favorable, and the reverse reaction is very, very unfavorable. And so we refer to some reactions as essentially irreversible, though it's really the balance between whether it's more left to right versus right to left. But in reversible reactions, these things pretty much balance each other out. As A and B are starting to react, these are just generic things, as they're starting to react to make C and D, well, at the same time, C and D are bouncing around in the flask, and they can react to make A and B. And when the rate of the forward reaction equals the rate of the reverse reaction, you come to a point called equilibrium. At equilibrium, the ratio of the concentrations of the compounds becomes constant. Just like if we had a bunch of people in this room and there were two doors, one for people to come in and one for people to come out. If one person was entering the room each minute and one person left the room each minute, an hour later, there's still going to be the same number of people in the room. It's just 60 people have come into the room over the course of that time and 60 people have gone out. So the molecules at equilibrium are changing constantly, but the overall ratio of what's present is staying the same. In that overall ratio, which is the ratio between the concentration of the things on the right divided by the concentration of the things on the left, is equal to what's called the equilibrium constant. The equilibrium constant is related to the difference in energy between the products and starting materials. So I guess I could have put another equation here to say that delta G equals negative RT times the log of the equilibrium constant. Again, I don't want to belabor these things mathematically, but just know that there is a relationship where if the things on the right are more stable, at equilibrium there will be more of those. If the things on the left are lower energy, more stable, at equilibrium there will be more of those. And the delta G, the difference between the energy of starting material and product, will be related to how much more there is of the thing on the left or the thing on the right. Le Chatelier's principle says that we can tweak the equilibrium. That is, if I add more A, for instance, I'm going to push this reaction and end up making more of this. On the other hand, if I add more C or D, I'm going to push the reaction to the left and end up getting more A and B in the end. Okay, let's look at some reactions. In organic chemistry, there are approximately 8 fundamental mechanisms, depending on how you define things. That is, we will look at reactions as either fundamental or combined. I'll get to combined mechanisms in a bit. But of the 8 fundamental mechanisms, you learned 4 of them last semester. We spent time talking about proton transfer, that's acid-base reaction, substitution, elimination, and addition, and I'll show these on a subsequent slide. This semester, we'll look at a couple of other types of fundamental mechanisms, radical and paracyclic. At least we'll spend a fair amount of time on one particular paracyclic reaction. There are a couple of others, electron transfer and transition metal containing steps, which we'll mention briefly like twice. So I'm not going to spend much time on those at all. But these fundamental steps in the left-hand column that we learned last semester are going to form the basis for much of organic chemical reactions, as I'll describe in a bit. First, let's do a real fast run-through of those. One of the first reactions you learned, probably the first, depending on who was teaching the class. If you had me, this is where I started, was proton transfer. That is an acid-base reaction. Here's a real simple example of an acid-base reaction. A hydroxide molecule reacts with HCl, or hydrochloric acid, to make water and chloride. Acids and bases can be described in 3 different ways, 3 different definitions: the Arrhenius, the Bronsted-Lowry, and the Lewis definitions. Arrhenius defined acids and bases in terms of the overall concentration of either H3O+ or HO-, hydronium or hydroxide. And Arrhenius said an acid is something that when you put it in water, you get more H3O+. So for instance, Arrhenius would say HCl, hydrochloric acid, is an acid because when you dissolve HCl in water, you end up getting a lot of H3O+. On the other hand, hydroxide, like sodium hydroxide for instance, is a base because when you put it in water, you get more hydroxide. I don't go into it on this slide, but there is also a relationship in water between hydronium and hydroxide. and their ratio, because they are in equilibrium as well. Bronsted and Lowry looked not at sort of the overall concentrations of things, which is what Arrhenius did, which is really a bulk property. But Bronsted and Lowry looked directly at the reaction itself. They said, what's happening in this reaction? And one way that you can look at how this reaction is changing is if you note there's a hydrogen that moves in this reaction. This hydrogen here is at the start attached to chlorine and at the end attached to oxygen. So Bronsted and Lowry said that an acid is something that gives up a proton, a positively charged hydrogen nucleus, H+, in the course of a reaction, and a base is something that takes in a proton. Or they would say a acid is a proton donor and a base is a proton acceptor. In this case, HCl acts as a proton donor because that's what gives up the hydrogen, and hydroxide is the proton acceptor because at the end that's what gains that extra hydrogen. Lewis looked at the same reaction and didn't focus so much on the atoms, on the nuclei, but instead focused on those bonds, the electrons. We know that Lewis was very interested in electrons. And Lewis said, well, we could focus in this in terms of the electrons. In this reaction, the oxygen has a lone pair that reaches out to make a connection to hydrogen. And since hydrogen can only have 2 electrons around it, at the same point, we have to break a bond. And so these 2 electrons that start out shared between hydrogen and chlorine get shifted over to chlorine. This curved arrow notation is how we show this in organic chemistry, and these curved arrows mean a pair of electrons starts here and goes here. This pair of electrons starts here and goes to chlorine. And Lewis defined this reaction in terms of that movement of electron. The thing reaching out with a pair of electrons to make a bond is called the Lewis base. The thing that is being reached out to is the Lewis acid. Or the way it's usually described is a Lewis base is an electron pair donor and a Lewis acid is an electron pair acceptor. This, by the way, is a mechanism. A mechanism is a detailed description of how the bonds change in a reaction. In this case, we see that this is a one-step process because I only show one mechanistic step. If I had a multi-step process, we'll see some in subsequent slides, I would have an arrow and then I'd have some intermediate and then I'd have some other curved arrows showing to the next step. A mechanism always shows all the electrons, includes things like pluses and minuses in this case, and shows curved arrows to show the movement of electrons. That's what a mechanism is. We will write many mechanisms over the course of Chem 3, as hopefully you did over the course of Chem 2, because to understand how and why reactions happen the way they do, you're going to have to understand the order of bond breaking and forming, and understand why that happens in the way it does. I'm going to pretty much focus on mechanism throughout. A couple of other terms. Here is our conjugate acid and conjugate base. The conjugate acid is what happens when I take the base and I add a proton to it. So hydroxide is a base, but if I add an H+ to hydroxide, I get H2O. And so water is the conjugate acid of hydroxide. The conjugate base is what I get when I take the conjugate acid and I remove a proton from it. So HCl is my acid, the chloride ion is the base. Is the conjugate base. If I was to do the reverse of the reaction, if I was to go from water and chloride to hydroxide and HCl, this would end up having to give up a proton and this would take in a proton, so this would act as an acid and that as a base. Last semester, we spent some time comparing acids and deciding some were stronger and others were weaker. And we ultimately decided that that had to do with the relative stability of the conjugate base. HCl is a very strong acid. That is, it completely dissociates when you put it in water. And the reason for that is because when you do so, you make chloride, and chloride is particularly stable. The relative stability of conjugate bases is what helps determine which is the strongest acid. There are different reasons why a conjugate base might be stable. I'm just going to mention them. You might want to go back and look at this if you don't remember this at all, but the stability of conjugate bases could be related to electronegativity or size. It could be related to resonance. In a few cases, we'll talk about the importance of hybridization to the stability of a conjugate base, and I hesitate to mention it because it is so unimportant and tends to confuse students rather than enlighten them, but there's something called an inductive effect. Don't worry too much about that. It's a very small effect. Certainly something like resonance is extremely important in describing the relative stability of a conjugate base. Okay, our next fundamental mechanism was substitution. From the standpoint of an organic molecule, a substitution reaction involves losing one atom or group of atoms and replacing it with another atom or group of atoms. We saw that there were two main mechanisms for substitution. There's the SN2 reaction and the SN1 reaction. It's a little bit confusing in that the SN2 reaction is a one-step process, as shown here, and the SN1 is a two-step process, because the names actually come from the kinetics. An SN2 is a second-order reaction. That is, in the rate-determining step, which in this case is the only step, there's only one step here, there's two things present, both a nucleophile and a substrate with a leaving group. In the SN1 reaction, on the other hand, the first step turns out to be rate determining, and notice in the first step there's only one thing present, this molecule with a good leaving group. Let's talk our way through these mechanisms quickly. In the SN2 reaction, you've got some nucleophile, and we spent some time talking about what makes a good nucleophile, but it's essentially a Lewis base, an electron pair donor. Reaches out to make a bond to carbon. But carbon can only have 8 electrons. Remember, this carbon has 8 electrons around it because there are 2 implied hydrogens. And so if I'm going to make a bond, I have to, at the same time, simultaneously break a bond. So if I have a good leaving group, and a good leaving group is similar to a relatively stable conjugate base. So these discussions are very similar, and we followed this directly after talking about acid-base chemistry last semester. If I have a good leaving group, that will go away. There are some other details to this. Last semester we talked about what the transition state looked like. We talked about the inversion of configuration. If this was a chiral center, that would have some consideration in this. And we talked about the fact that the solvent doesn't really affect this reaction very much. But most important thing to know is this happens with strong nucleophiles and good leaving groups at sterically unhindered positions. What do I mean by that? I mean positions that aren't very crowded. So primary positions work very well for the SN2 reaction. On the other hand, the SN1 reaction happens in 2 steps. In the first step, a leaving group goes away, so a bond is broken, and some good leaving group floats off with a pair of electrons. But if this bond is broken and the electrons go with the leaving group, that means this carbon lost electron density, so we make an intermediate, a positively charged intermediate, carbocation. That carbocation wants electrons, and so some Lewis base comes along, which we're going to call a nucleophile, comes along and interacts with that carbon to make a bond. Now, this happens best at tertiary positions, such as, T-butyl bromide or something like that. And the reason for that is because you make a carbocation here, and when we talked about reactive intermediates last semester, we talked about primary versus secondary versus tertiary, and we found out that tertiary carbocations were more stable than secondary, and secondary were more stable than primary. In fact, primaries are not formed under normal conditions. Also, since we're forming something charged, solvent matters quite a bit. Polar solvents will help promote the formation of charged species, for the same reason that salts dissolve in polar solvents. If you take sodium chloride, you mix it in water, it'll break apart into the sodium plus and chloride minus, because there are favorable interactions between the polar water molecules and the charged pieces of sodium and chloride in that case. Same thing here. In polar solvents, these charged species can be stabilized by ion dipole interactions. This also tends to happen with weak nucleophiles, pretty much because strong nucleophiles will end up doing either SN2 or E2, which we'll get to on the next slide. You also get a mixture of stereocenters. This particular example is not chiral, but if I had shown you a chiral example, because carbocations are flat, and so a nucleophile could approach from in front of the screen or from behind the screen, which would give you opposite senses of handedness. Our next fundamental mechanism were the eliminations. The elimination reactions again came in two flavors: a one-step process, which is called E2, and a two-step process called E1. Again, the 2 and the 1 in the names E2 and E1 come from the kinetics. In the rate-determining step for the E2 mechanism, which is the only step since it's a one-step process, there are two things present: the base and some organic molecule with a good leaving group. In the E1, the rate-determining step is the first step, and the only thing present is the organic molecule with a good leaving group. In the E2 mechanism, a strong base reaches out to make a bond to a hydrogen. As a bond is formed to hydrogen, hydrogen can only have 2 electrons around it, so these 2 electrons have to go somewhere. They're going to end up getting shared between carbon and carbon. But this carbon can only have 8 electrons around it, and so I got to break a bond. So let's break a bond to a good leaving group. And the good leaving group floats away with its pair of electrons, giving a double bond in this example as the result. This tends to happen with strong bases and leaving groups at sterically hindered positions like tertiary positions. If you had a strong Lewis base and a leaving group at a primary position, that would tend to do SN2 reactions. If your leaving group is at a secondary position, it'll make you'll get a mixture, but some things tend to prefer substitution and others tend to prefer elimination. We can get into that in a little more detail if you want it at another time. In an E1 mechanism, the first step that happens is the leaving group leaves to make a carbocation. You might notice that this is the exact same step as the first step of the SN1 mechanism. In the SN1 mechanism, a Lewis base comes along and interacts with this positively charged species. But on the other hand, if your base comes along and interacts with the hydrogen next door, and if you make a bond to hydrogen, we got to break a bond, so these 2 electrons go somewhere, they end up making a double bond. But you're going to get a mixture, because the base could come up and interact here, or the base could come up and interact here. If it interacts here, you get substitution. If it interacts here, you get elimination. And you will generally get a mixture of things when you have SN1 and E1. With E2 and E1, there are also issues of solvent, because polar solvents favor the E1 and non-polar solvents. E2 is relatively insensitive to solvent. There are also issues of stereochemistry. The final fundamental mechanistic type that we covered in Chem 2 were the addition reactions. We'll spend some more time on these, by the way, I should mention, this semester. So if you don't remember all these details, that's fine. We'll get back to them as well. But in addition reactions, we start with a double bond and we add 2 groups. Contrast this with eliminations, where we took away 2 groups and we ended up with a double bond. So if we start with a pi bond and we add an electrophile to one end, and the electrophile that we'll very often use is something like an acid, though we will see other examples as well this semester. But if we start out with the pi bond reaching out to some electron acceptor, a Lewis acid, well, this carbon, there was a pair of electrons shared between these 2 carbons, and now the blue electrons are shared here. We end up with a plus charge on this position. This carbon needs electrons. If a nucleophile comes along and interacts with that position, we're going to get our our addition product. Notice I put the electrophile at one end and the nucleophile at the other. I didn't put the H here and the nucleophile here. And that has to do with the intermediate, which one is more stable, and that's called Markovnikov addition. We'll spend a little bit of time on this later on in the semester when we focus on alkenes, so I won't belabor the point right now. There's also nucleophilic addition. This happens not with just any old pi bond, but with polarized pi bond. And the most important polarized pi bond is a CO double bond. When you have a very strong nucleophile adding to a CO double bond, and a very strong nucleophile might be something like a Grignard. We talked about carbanions, Grignard reagents last semester. We'll come back to them again this semester. That nucleophile will end at the partially positive end of the CO double bond. And if a nucleophile adds here, well, this carbon can only have 8 electrons, so electrons have to go somewhere. 2 electrons will end up on oxygen to make an O-. O-, oxygen would really rather have 2 bonds and 2 lone pairs, so if that reaches out to some proton source, we'll end up with an OH group, which is the alcohol functional group. This is a great way of making alcohol functional groups, and when we talk about alcohols later on this semester, we'll spend some time on nucleophilic additions. Now that's it for the fundamental mechanistic types you learned last semester. Again, we will add a few other fundamental mechanisms, but not many. Most of what we'll learn this semester will be combinations of these same fundamental mechanistic steps to make new reactions. We saw a couple of these last semester. Let's just see what I mean. Here's an example of a reaction we spent a brief amount of time on last semester. If you had me, others might not have covered this, so this might be new, but that's okay. We'll spend some more time on this later. But I want to use this as a chance to introduce the idea of combined mechanisms and show you that they look scary. This is the Fischer esterification. But I'm going to try and convince you that they're not. Okay. This is the mechanism for the Fischer esterification, and notice it's 7 steps. I'm going to walk through them. At the start, you've got a carboxylic acid. You've got a carboxylic acid that reaches out, the pi bond of that carboxylic acid reaches out to make a bond to hydrogen, an OH bond. But if this shared pair of electrons between carbon and oxygen reaches out to become shared between oxygen and hydrogen, we end up with a plus charge on this carbon. This carbon wants electrons. An alcohol has lone pairs. This alcohol can act as a weak nucleophile and add to this position to make this intermediate. This intermediate has an oxygen with 3 bonds and 1 lone pair, a formal charge of +1. Oxygen doesn't want to have 3 bonds and 1 lone pair. It wants to be neutral, 2 bonds and 2 lone pairs. So let's break a bond. By the way, that's going to be a motif we're going to see again and again this semester. So if I break the OH bond, I'm going to end up with a oxygen with 2 bonds to carbon and 2 lone pairs. But this intermediate is still in the presence of acid, and these oxygen lone pairs can reach out to interact with more acid. By the way, I could reach out with these, either this or this, and because of symmetry they're the same, oxygen lone pairs, or I could reach out with this oxygen lone pair. If this oxygen made a connection to a hydrogen, we'd be back over here. But that's a reversible step. But you know what? This whole reaction is reversible. And every step is reversible. At this point, instead of breaking that bond, if I had broken this bond, I'd be here. At this point, if instead of having a nucleophile come along, I had taken away this hydrogen, I'd be there. So all of these steps are reversible. And in fact, the reverse process follows the exact same mechanism in reverse. We can drive that equilibrium by Le Chatelier's principle. So if I treat a carboxylic acid with an excess of an alcohol under acid conditions, I am going to make more of this. This functional group is called an ester. If I treat an ester with an excess of water under acid conditions, I'm going to push it back this way, Le Chatelier's principle, to make the carboxylic acid. Going from left to right is called esterification. Going from right to left is called hydrolysis. Water is hydro, and breaking bonds is lysis. So breaking a bond with water is called hydrolysis. Okay, back to this point of the mechanism. If this oxygen, or this because it's symmetrical, picks up a proton, we're going to get, again, oxygen with 3 bonds in a lone pair. Formal charge of +1. To satisfy that oxygen, let's break a bond. If I break this bond, what do I get? I get H2O, right? Notice loss of water, that's one of my byproducts in this reaction. Anytime I can break off a small molecule like water, that's going to be a pretty reasonable leaving group. But that's going to leave a positively charged carbon because I have a shared pair here. Those 2 electrons go to oxygen. That carbon is left electron poor. It wants electrons. If I break the OH bond next door, and those electrons end up shared between carbon and oxygen, I end up with my ester. Okay, that is 7 steps. And 7 steps seems very scary up front. But you'll notice on this slide I've highlighted the first 2 steps. A pi bond reaches out to make a bond to proton. You get a carbocation intermediate, and then a nucleophile comes along and adds. That should look familiar. On the previous slide, when we looked at addition reactions, that was our electrophilic addition mechanism. Okay, here it's a CO double bond instead of the CC double bond on the previous page. But even so, the arrow pushing is the same. A couple of steps on this process are simply a proton transfer, or a couple of proton transfers. First, we lose a proton from this oxygen, and then we put a proton on this oxygen. That is simple, straightforward acid-base stuff. Nothing exciting there, just another application of the fundamental mechanistic steps that we learned at first. These final, look what happens. First, a bond is broken, a leaving group goes away, we get a positively charged intermediate, and then we remove a hydrogen from the next position over. So something like, say, a water molecule comes along and pulls that off. I'm not going to worry too much about what pulls that off because it could be another molecule of the alcohol, it could be a water molecule, it could be a molecule of this, it could be the conjugate base of the initial acid. Something pulls off that proton and we end up making a double bond. But that's just the E1 elimination. Leaving group goes away, positively charged intermediate, loss of a proton for the next position over to make a double bond. And so this complex, this 7-step process, 6-step process, I've said 7 several times now here, haven't I? This 6-step process comes down to just a combination of the same fundamental mechanistic types that we learned at first. In this particular case, we see electrophilic addition reaction, we see proton transfer steps, and we see E1 elimination steps. Again and again and again, this semester, we will see reactions that come down to combinations of the same fundamental mechanistic steps, mostly proton transfer, addition, elimination, and substitution reaction steps. As I noted, we will see a couple of additional fundamental steps, but mostly we're going to see combinations of the same fundamental steps. One more example. Last semester, we learned about oxidation reactions. By the way, this is something in particular that you might not have covered at another institution in the first semester. Your other institution might cover this in the second semester, so this might be something in particular you want to go back and look at and come talk to me if you have any questions about it. But we learned about oxidation reactions involving chromium agents. There are 2 particular chromium agents we used, PCC, which is called pyridinium chlorochromate, and chromic acid, H2CrO4. We saw that alcohols could be oxidized to make functional groups containing CO double bonds. In particular, secondary alcohols can be transformed into ketones. That's the example I've shown on this slide. Primary alcohols, depending on which of the 2 oxidizing agents you use, could be oxidized to make aldehydes or carboxylic acids. Now, I want to look at the mechanism of PCC oxidation of a secondary alcohol. if this case, in this case this is isopropanol, also known as 2-propanol, is treated with pyridine, hydrochloric acid, and CrO3, chromium trioxide. That's what PCC is. It's just an abbreviation for this combination of reagents. Pyridine is simply a base that will act as a proton transfer agent. You will make acetone, which is also known as 2-propanone. What's the mechanism of that? Well, here it is. It's a 4-step process, so it might look a little scary. Chromium's a little different than some of the other reagents that we've used, but I want to show you that this is simply a combination of the same fundamental mechanistic steps. First, what do we see? The first 2 steps come down to an electrophilic addition, going from here to here. When chromium trioxide is mixed with HCl, we've got these pi bonds. They're chromium-oxygen pi bonds, but they're still pi bonds. A pi bond, when it's around some acid, some electrophile, HCl is an acid, it's a source of H+, the pi bond can reach out to that H+ to make an oxygen-hydrogen. But we end up with a positively charged center, because chromium lost electron density in that deal. And so some nucleophile, and this alcohol is going to act as the nucleophile, is going to come along and interact with chromium. Notice this is just an addition across a chromium-oxygen double bond. First the pi bond reaches out to the H+, and then a nucleophile comes along. That'll give us this intermediate. I apologize, there should be a plus charge on this oxygen. I will fix that in the handout that I post online. But for this recorded lecture, just realize that there's a positive charge here because oxygen has 3 bonds and 1 lone pair. Oxygen with 3 bonds and 1 lone pair is unstable. Let's break a bond. If I broke this bond, I'd go back there. But if I broke this OH bond, those electrons would end up on oxygen, so I'd get here. That's just proton transfer. That's just an acid-base step. And then what about this last step? Kind of the key step, the irreversible step, it turns out, is pyridine acts as a base. It comes along, it grabs this hydrogen, electrons get shared between carbon and oxygen, and an oxygen-chromium bond is broken. You know what? Just an E2 elimination. This is just the leaving group. Don't worry for the moment about the fact that don't worry at all, really, about the fact that it's chromium as a leaving group instead of something like the chloride or, halide or tosylate or something that you might have seen in other E2 eliminations. Just think of this as a big leaving group. And pulling off a hydrogen, making a double bond, and kicking out a leaving group, all in one step, that's an E2 elimination. So this complex-looking process, in this case 4 steps, turns out to just be a combination of electrophilic addition steps, a proton transfer step, and an E2 elimination step. Again, almost all the reactions that we see this semester are going to be just new combinations of the same fundamental steps. So I definitely suggest you might want to just go back and remind yourself of proton transfer, acid-base stuff, the substitution, that is SN1 and SN2 mechanisms, the elimination, the E1 and E2 mechanisms, and the addition reactions, the electrophilic and nucleophilic addition reactions. I'll certainly remind you of these things as we come to them, and we will spend a fair amount of time on some of those this semester. But those are going to form the basis for pretty much everything else. All right, that's our whirlwind review. So in 2 lectures, I went through all of a semester of organic chemistry. Hopefully that jogged your memory. If there are things that you need to review, I suggest that's a good sort of indication of what things were most important from last semester that we're going to continue on with this semester. Come to office hours and talk about these things by all means. Look at your text, look at your notes if something's unfamiliar. And next time, we're going to start moving on to new material. in our next lecture, we're going to start in on our first major new section of organic chemistry, and that is we're going to look at spectroscopic techniques. All right, thank you so much.